Hello everyone, this is lecture 13, Limits and Continuity. So far we have seen the example of functions of several variables, but calculus has not yet been entered the picture. So in this section, we revisit topics encountered in single variable calculus, such as limit, continuity, derivative, and integral. More specifically, in this lecture notes, we want to go over the concept of limit and continuity. So hopefully at the end of this lecture, we would be able to understand the concept of limit of functions of two variables. In particular, we could be able to perform calculation on limit of the function using limit laws, and we could learn how to determine the existence of limit of functions of two variables, and we will hopefully understand and state conditions for continuity of a function and apply that to verify the continuity of function of two variables at a point. So in single variable calculus, you learn about limits of functions, and more often you are introduced to the topic by given a definitions of following statement. That is, suppose the function f is defined for all x near a except possibly at a. If f of x is arbitrarily close to L as we like, for all x sufficiently close but not equal to a, we can write that limit of the function as x approaches a equal to L, for L is the limiting value. And we say that the limit of f of x as x approaches a equals L. So this definition is a definition, but is a very vague definition because it does not really tell you how close is arbitrarily close or how close is sufficiently close. Therefore, later on, they move on to introduce to you a more precise definitions of limit of single variable functions. That is, let f be a function defined on some open interval that contains a number a, except possibly at a itself. Then we say that the limit of f of x as x approaches a is L, and we write the statement in terms of a formula here. If for every number epsilon greater than 0, there is a number delta greater than 0 such that the distance between x and a is greater than 0 and less than delta, then the corresponding distance between f of x and the limiting value is less than epsilon. So by using this definitions, of more precise definitions of limit of a function, it tells you that you can more precisely define the distance between x and a, and in turn give the distance between the function and the limiting value. And the value of epsilon when you do this kind of calculations usually referred to as the error tolerance. Now let's take a look at the following image. You have an arbitrary functions of the form y equal to f of x. In order to find the limit of the function as x approaches a, you want to find the distance between x and a, such that the distance between f of x and the limiting value is actually within the error tolerance that you may allow. And you could be able to come up with this value on the x-axis and this value on the y-axis by solving the inequality of the distance between x and a. You have that x minus a is greater than negative delta and less than positive delta, and you want to know what is the interval of x such that x is close enough to the value a by adding a on every term in the inequality. So you get a minus delta less than x less than a plus delta. So therefore, this is the interval on which x is close enough to the value a. Similarly, when you solve for the distance between f of x and the limiting value, so when you solve for this, you get negative epsilon less than f of x minus L less than positive epsilon. And you want to know what is the interval of f of x such that f of x is close to the limiting value. So you add L on every term inside the inequality and you get L minus epsilon less than f of x less than L plus epsilon. So these calculations tell you that if x falls into this interval, that guarantees us to find the limit. Now, as an example, we would like to consider the following functions. You have the piecewise defined functions of the form f of x equal to 2x minus 1 as x different from 3, and f of x equal to 6 as x equal to 3. So this is the graph of the functions. You notice that at x equal to 3, the function is defined and the output is equal to 6. Now, intuitively and by our experience in finding the existence of the limit of a function in single variable calculus, you see that the limit of the function exists and is equal to 5. That is, the left-hand limit equal to the right-hand limit equal to the same value. In this case, is 5. Therefore, the limit exists and the limiting value is 5. Now, to precisely determine the distance between x and a, for a is 3 in this case, and the distance between f of x and the limiting value 5, if you do some calculations to determine the value of delta and epsilon, you may arrive at the following result. That is the distance between f of x and the limiting value 5 less than 0.1. If you have the distance between x and 3 to be 0.05. If we change the number of 0.1 in our problem to a smaller number, such as 0.01, we can calculate that. So in this case, f of x minus 5 less than 0.01. We can calculate that the distance between x and 3 is going to be 0.005. Similarly, if we change the number 0.01 to a smaller number, such as 0.001, we can calculate that the distance between x and 3 is less than 0.0005. So again, the numbers that you see 0.1, 0.01, and 0.001 that we have considered are error tolerance that we may allow in our calculations. Not only that, we can bring the difference between f of x and 5 below each of these three numbers, 0.1, 0.01, 0.001. We must be able to bring it below any positive number that we can think of. And by the same reasoning, we can. If we write epsilon for any arbitrary positive number, then we find as before that f of x minus 5 less than an epsilon if the distance between x and 3 less than delta. For delta, if you do a calculation, you will see that is going to be equal to epsilon divided by 2. So the statement in pink is a precise way of saying that f of x is close to 5 when x is close to 3, because the statements say that, or the formula say that, we can make the values of f of x within an arbitrary distance epsilon from 5 by taking the values of x within a distance epsilon divided by 2 from 3. So doing these calculations, or we cover this kind of topics in order to give us a more precise way to determine the distance between x and a and the distance between f of x and the limiting value, or tell you what is the error tolerance that you may allow the calculations to be. So that is the limit of single variable functions. We can give a similar definitions of limit of functions of two variables as follow. So the function f has the limiting value L, and a point P x y approaches the point P0 AB, written in the form of limit of f of x comma y as x and y approaches a and b, is equal to L. Given any epsilon greater than 0, there exists a delta greater than 0 such that the distance between the function and the limiting value is less than epsilon whenever x comma y is in the domain of f, and the distance between the point x comma y and the point a b is greater than 0 and less than delta. So the square root that you see in this inequality is the distance between p and p0. Given that p is equal to x comma y and p0 is a comma b, so when you do the distance between p and p0, we get the square root formula. By definitions of function of two variables, the domain of the function consists of all the point x comma y in R2 such that x and y satisfy certain conditions, as we covered in the last lecture. Similar to functions of one variable, we have that the distance between the function and the limiting value is less than epsilon if the distance between the 2 points is less than delta. You notice that the square root of x minus a squared plus y minus b squared less than delta, and then you square both sides of this inequality, you get x minus a squared plus y minus b squared less than delta squared. So it say that the distance between the function and the limiting value is less than epsilon if the point x comma y is within the circle center at point a comma b with radius less than delta. So let's visualize the concept here. So you want to find all the point x comma y within this circle center at the point a comma b with radius delta. And for each point in the circle, you can map it to a corresponding z value, or the output of the functions. And the output value has to be within the interval of L minus epsilon and L plus epsilon in order for us to be sure that the limit exists and we can calculate the limiting value. And this image is a three-dimensional view of what we are talking about. Again, you want to find a point, all the point x comma y within the circle center at a comma b with distance delta such that the corresponding output value has to fall within the interval L minus epsilon and L plus epsilon so that the limit exists and we can identify the limiting value. So for function of one variable, the limit exists when the left-hand limit equal to the right-hand limit equal to the same value. However, for function of two variables, as you can see, that you identify point inside a circle. Therefore, there is infinitely many paths going from point on the circle to the center of the circle. Therefore, identifying the existence of the limit for function of two variables is a little bit more challenging. It requires a little bit of work before we can get to the answer. And we're going to look at some example later on in this lecture. This is the visual demonstrations of what I just mentioned. That is f of x comma y approaches L as p approaches p0 along all paths in the domain of the function in order to conclude that the limit exists.